Hello again. Tonight we're going to talk about sunspots on our sun, or as I've discovered by journeying down the rabbit hole, they're actually plasma sinkholes on the sun. We'll get into the details. So, what are sunspots? The sun is a star. There's lots of them out there, but the sun is our star. Stars are nuclear fusion engines. Stars that are younger or midlife, like our sun, they burn hydrogen and then helium in their fusion furnaces, and they release intense amounts of plasma, electrically charged gaseous material. And it's released at high energy and high pressure. And it's what's the outer surface of the sun is just a giant ball of plasma. And this circulating plasma generates massive electromagnetic fields because plasma is ionized. And these fields inhibit convection. So they hold things in. And when a couple of these fields get together and entangle upon one another, and the lack of convection can actually cool down an area of the sun. And it's what is known as corralled plasma. So the magnetic field gets wrapped around itself and holds the plasma beneath it in a constrained area, and therefore it cools down. And as it cools down, we get these things called sunspots. They're not actually spots on the surface of the sun. They're not defects, as a public observer once said. Are those defects on the sun? No, they're not bruises on the sun either. They're very normal. They're just as a result of electromagnetic fields generated from plasma getting entangled and corralling plasma. So there's lots of different things going on in the sun. They're all kind of related to plasma and electromagnetic fields, but they have different behaviors. So we'll focus on sunspots, but I'll mention the others. When the surface of the sun wants to actually shove plasma out electrically, because it's electrically charged, it shoves it out in these very high arcs. But because the mass of the sun, the gravity of the sun is so huge, even the light, wispy plasma that's energized gets pulled back down to the surface of the sun along the magnetic field lines. So these are coronal loops. That's the second picture. You can see why they call them loops, because they're giant loops. Then there's the flares or filaments or prominences that you normally see coming off the side of the sun. They come off 360 degrees around the sun, but it's easiest to see them if you block the sun with a disk or during a total eclipse like we had recently. You can see these plasma plumes coming off the sun. But once again, they don't have enough ejection force to actually leave the sun. They sort of go out and then fall back into the sun. They look like lava streaming out from a volcano without any smoke, and then the lava falls back almost where it came from. And when the magnetic field lines snap, or when they're side-by-side magnetic field lines, if there's not sufficient energy to eject plasma along them, then you'll get what is known as a reconnection. Two, like spitting out electromagnetic curves, will find that they'll like hook back together, and you get a reconnection of the broken magnetic field lines. And then if you have enough energy in the field lines to actually accelerate plasma to get it to overcome the gravity of the sun, then the plasma will actually leave the sun and go out into space. And this is called a coronal mass ejection. And there were two that happened this week. If there's a CME and the CME is observed when we're facing the Earth, that CME will never strike the Earth, because when the CME comes out of the sun, because the Earth is moving around the sun and the sun is rotating with high mass object rotating, there's a lateral velocity associated with the CME. And so it'll fly off sideways into space rather than hitting the Earth's magnetic field. If there's a CME observed by like SOHO, and it's on the far side of the sun, when we observe it, there's a higher probability it's actually going to encounter the Earth's magnetic field. And when it does, that's how we get auroras. most people don't get to see a close-up look at the sun, particularly sunspots or granules, those little polygonal shapes, or when there's a bunch of them off in a direction that makes the sort of light-colored streak across the surface of the sun called plage. The sunspots actually are temporary. They come out of nowhere, so to speak, when the magnetic field lines get bunched up. They grow, maybe split up, maybe join together, but eventually there's not enough energy to sustain them, so they kind of dissipate and fall apart. And you can see on the left side here, there's a bunch of chunks of that sunspot material that are leaving the sunspot. Now, this is a GIF image. It's an animated GIF image, which unfortunately Zoom doesn't show those in backgrounds of PowerPoint presentations. But if you follow the links at the end, you can actually find the link to the GIF for this that's in the Sunspot Wikipedia link down towards the bottom. And the video is very interesting to watch. I've observed this through my personal telescope, myself, and at public events. And literally, you can see plasma rolling inwards along these sort of feathery lines around the edge. The plasma rolling inwards into the black area. So sunspots are dynamic. They come out of nowhere. It can be like a slew of them stretching out across the rotation of the sun. And then they can like gather together, clump up, spread apart, and then just gone. There's no real prediction as to when a sunspot comes into existence, how big it's going to get, or how long it's going to last, or whether it's going to join up with others. But if you're really interested in sunspots, this is a very amazing video. I think it was taken by Soho. So this was the part that I had seen in my observing with a white light filtered telescope, not even a hydrogen alpha, is that when I was looking at the sunspot dead on to the sun, it would look kind of flat. But as the sunspot moved around, or if it came from one limb of the sun, one edge of the sun, and moved to the other edge of the sunspot took on the appearance of depth. And if you caught the sunspot at just the right angle, right at the edge of the limb of the sun, you would actually see an indent in the surface of the sun. So I've always stated sunspots are indents in the sun. And the reason why they're indents is the plasma on the surface of the sun is so hot that it's always churning, boiling, bubbling. But as soon as you have the magnetic field lines tangle up and you drop the temperature in the sunspot umbra, the center of the sunspot, the dark spot, by hundreds or maybe a couple of thousand degrees, that's a lot of energy loss and contraction. And where is it going to go? Because remember, the plasma is flowing in from the edges. So it's not going to like flow out over the edge because it's got too much to resist. It's like asking for a volcano to suck the lava back in. It's not going to happen. It's got to come out. It's got to go where there's path of least resistance. And because it's cooled down, the path of least resistance is back into the sun. And it turns out that the umbra, that dark area of the sunspot, is about 600 kilometers or 370 miles indent into the surface of the sun. And because it's indented, that's also what allows the plasma to want to flow into it. Is you've got a well, you've got a sinkhole. And the actual structure of a sunspot, because the magnetic field lines go so deep into the sunspot itself, not the depression well, but the actual convoluted magnetic structure of the sunspot, is thousands of kilometers beneath the surface of the sun. And you have an image on the left there that was taken from different slices of energy levels of the sunspot, and they could see how it grew from the outer to the inner to the inner. And that allowed them to understand that the magnetic field lines that are bunched up are actually stronger towards the center, kind of like the top of an umbrella. And that pushes the sunspot down into the sun by thousands of kilometers. That's okay, the sun can take it. It's a lot larger than thousands of kilometers. So sunspots move. Sunspots have their own velocity when they first form, they're under 1,000 miles an hour, hundreds of meters per second. But the sun rotates. And every 24.47 days, from the Earth's perspective, the sun does a 360. So if you have a sunspot that is rotating with the plasma flow because it's closer to the equator than the pole, then the sunspot will actually move across the face of the sun in a few hours. And I've watched this as we've observed the sun during public solar observing events. Hey, look, there's a sunspot on the incoming side of the sun, and we're going to do a 4-hour event here. So over the 4 hours, we get to watch the sunspot slowly creep to the other side of the sun. They don't go horizontally across the equator. Because they're coming out near the equator, they kind of bubble up and want to arc upwards towards the North Pole or the South Pole, depending upon the axis. And so you'll see them start out in one spot and then have an upward curve to their motion, which means they're getting their own momentum plus the rotational momentum of the sun itself. So the sunspots go through an 11-year solar cycle. There's a minimum called the Maunder minimum, when there's the fewest sunspots, and then you have the maximum, which doesn't have a name, but that's when you have the most sunspots, and we're closing or about on the maximum. When they talk about how many sunspots are on the sun, as a public observer of the sun, when we're a Maunder minimum, I can go to public observing events where, I'm sorry, with my telescope, there are no visible sunspots. Very depressing. Or right now, like when we did the partial solar eclipse at MODS, there's lots of sunspots out there, and they hang around and they're big. You might also hear the phrase star spots. When people first hear about star spots, okay, sunspots are in the sun. There's billions of other stars out there. What you're looking at called star spots, they must be sunspots on those other stars. No, sunspots appear large compared to the diameter of the Earth, but sunspots on other stars will be so infinitesimally small and dim that we could not actually see them from any of the instruments we have from Earth. So star spots are literally thickened areas of plasma, rock, or dust or debris that is many, many, many times larger than a sunspot. They're like larger than planet size, and they're just a batch of thicker stuff around that distant star, and that causes that star to dim in that region. Then there are variable stars that's a whole nuclear furnace kind of variability thing. People will often ask, why are sunspots black? Well, first off, they're not black. The protective solar filters that we put on telescopes block out all but the brightest light, which is also why when the sun goes behind clouds, you can no longer see the sun through a white light filtered solar observing telescope, because the sun is no longer bright enough to make it above the filter threshold. Anything dimmer than that filter threshold is just black. So while sunspots may not be the brightest part of the sun, they're still very, very bright, very hot, just not bright enough to cross that threshold. So instead of appearing bright on the sun, which would make them difficult to see, they appear dark on the sun. And they're maybe a few thousand degrees cooler than the surface plasma, but they're just not bright enough. Therefore, they're black. Well, they appear black, but they're not. I have a filter that I used during the partial solar eclipse called a solar continuum filter. It's specifically designed to let a little more light in, but not in the ultraviolet or infrared ranges. It lets it in the green range. So it allows you to have a higher contrast on the sunspots, and you can very much better see that influx of plasma into the umbra of the sunspot. So how large are sunspots? Well, I found this one out going down the rabbit hole. The smallest of sunspots are only visible from space probes observing the sun. They're not visible from the Earth at all, no matter how big your telescope, because some sunspots are very, very tiny. You can only see them with things like the Parker Solar Probe that is zooming past the sun in ever-tightening orbits, where it might be only a few hundred miles above the sun, but it's moving at a very, very fast speed, so it has to take a very quick picture. And it can see sunspots that are smaller than what we normally see with like SOHO or telescopes from the Earth. So when you think, oh, there's not that many sunspots on the sun, you're not counting all the hundreds of them that are just too small to be seen. But typically they're larger than the Earth, and the largest groupings of sunspots are many times larger than the Earth. And for perspective, I took one of the SOHO sunspot images and I plopped down a little gray circle that's roughly the size of the Earth. Sunspots be big. So how do you observe sunspots? The best place of all, unless you're into the personal gratification of observing them live, on the internet. NASA, the European Space Agency, and others have all kinds of probes out there. They have dedicated telescopes for just staring at the sun, and they have all the latest images. In fact, if you just Google solar weather, you'll find that NASA maintains a daily solar weather forecast. It will tell you coronal mass ejections, sunspot activity, if there's anything that may be a CME, may be energetic enough to be a CME. They'll show you pictures of it. Not just pictures, they make videos, like 8-hour slice videos, and they'll show you videos of it. Not just in visual light, but in infrared and ultraviolet and X-ray and visible. But if you want to look into getting a telescope, my recommendation is go with binoculars and just buy filters for your binocular. But if you have a telescope, you can buy a filter that goes on the front of the telescope that looks mirrored or silvered, and it just sort of nylon screw, press, tighten onto the front of your telescope, onto the view shield, and that will block out the majority of the light, all the UV and most of the IR, and a little bit of the hydrogen alpha going back towards the eyepiece. And then you probably want to throw on something that counters the coloring of your filter. If you're going to buy one of those filters, I'd say buy it in just black and white, gray, because then you can put whatever color filter you want on the eyepiece. So if you want to show it off to an elementary school, you can put a yellow, nice deep yellow filter in there and show them the Crayola yellow sun that they expect. Or you can use a solar continuum filter and the sun comes out green, and then you have to explain to people how in space the sun is actually very light green. But if you want to see flares, prominences on the side of the sun as they erupt, then you need a hydrogen alpha telescope. It's the personal solar telescope, the PST, by Sky and Telescope /Meade/Coronado. I think it runs you around $700 or $800. It's a very small diameter telescope because the sun is big and bright, but the hydrogen alpha is a very, very deep red color. The human eye does not see that well in deep red. It would be interesting for them to make a hydrogen alpha scope that does what a green laser pointer does. Put that in the eyepiece, and the infrared light would be converted to green light. It does a energy reduction. It takes 2 photons of infrared, adds them together, and comes out with a shorter wavelength, higher energy photon in the green area. Someday they'll figure that out. But yeah, I've watched solar prominences actually spewing off the sun in real time through an HA scope, not this one, but a bigger one. And even to see that in the daytime, we had a black sheet that you threw the black sheet over your head and the telescope in order to get it dark enough for your eye to open up to see the dark red light. But if you want more information about the sun, the NASA JPL Night Sky Network site has a good presentation on all those aspects of the sun called Our Magnetic Sun. It's one of their kits, but if you want to get the information and download the poster so you can read it, that's available on the Night Sky Network website, and there is a link at the end of the presentation that includes that. So in conclusion, our sun is a star. It's a fusion furnace generating plasma as it consumes hydrogen, eventually helium. The plasma circulations, because plasma is electrically charged, generate magnetic fields as they swirl around at high speed. These fields can become entangled or corralled, and that prevents convection. And by preventing convection, that area will get slightly cooler, which makes it slightly dimmer than the rest of the surface of the sun. And there you have your spot. While it's darker enough to not be visible in a filtered telescope, so it will appear black. But I always like to tell people it's the second brightest visual part of the sun. The plasma is the bright part you see, and the next brightest part is the sunspots. They're temporary. They rotate with the sun. They grow, they shrink, they move around, they separate out, they join up, and eventually they disappear. But there are other effects on the sun that have to do with plasma and electromagnetic fields. These are loops, flares, and coronal mass ejections. They can be observed in personal telescopes with either a white light filtered scope, which is my recommendation, or a hydrogen alpha scope, which is, you can look at coronal mass ejections and prominences, but you got to spend the money. And always, never look at the sun directly. I don't care if it's eclipsing or what, but the sun is very bright. Don't stare into the sun, even if it's during an eclipse. Always either look through something like a telescope or a video of a camera. You know, your eyes have to last a lifetime. Okay, a couple of pages of hyperlinks here. And the actual depression into the sun by the umbra of the sunspot is called the Wilson effect. The guy whose last name was Wilson first said, yeah, that's what it is. And he was only referring to when a sunspot is straight on at you, it looks flat. As it gets around to the limb of the sun, it looks indented. It looks 3D. And then we get into all the other things, coronal loops, prominences, reconnections, CMEs, the SOHO image, courtesy of the European Space Agency, of the subsurface structures of it, and then our magnetic sun on the Night Sky Network. Comments, questions?
Is it known yet why the corona and the chromosphere is so much hotter than the surface of the sun? I Googled it earlier, and it seems like it's still not known for sure.
It is still not known for sure. There's a couple of postulations, but we don't have any scientific data to corroborate either of those postulations. But it is many millions of degrees hotter above the plasma than the plasma itself. And it borders on being like the temperature at the core of the sun, but it's above the surface of the sun. There are people saying things like, you know those magnetic field lines, they've really got a hold on the convection of the sun. So rather than the heat being released from the sun, the convection is constrained by the magnetic field, and therefore the area above the plasma, above the liquid part of the sun, before it can escape beneath all of these loops, it just adds and adds and adds and adds the heat that can't be convected away. That's one of them. And the other one, I don't even remember it, but it seemed less plausible. Magnetic field lines of charged plasma, don't think of kilowatts or megawatts, think of terawatts. So it is a lot of electrical field energy, and we've just never been able to create that level here on Earth. We've gotten to gigawatts on things like particle accelerators, but we've never done that to any larger scale of just a plasma. We've done it with individual protons, but not with like a chunk of plasma. So we don't have any evidence Earth-based that we can do it until maybe we, start a fusion reaction that's sustainable. And then we can maybe see it within the magnetic field that the plasma is of a certain temperature, but the inside walls of the chamber have to be quite a bit more sturdy. But until we either create craft that can synchronously orbit the sun, in other words, like geosynchronous orbiting the Earth is you're always above the same spot as the Earth rotates. If we ever put a craft into orbit about the sun at whatever distance that it's not going to be nearby, it's going to have to be very high altitude, so that it can constantly observe an area of the sun and make all these measurements and watch a sunspot actually form and move out from underneath it, so you can see the transition. You won't know what is the source of all that heat, but you'll know that when the sunspot appears beneath you, that heat's going to die down because of the entanglement of the magnetic field lines. So if you want evidence of it, that's indirect evidence of it. So was there anything anybody learned from the presentation that they didn't already know about sunspots?
Well, I thought those cooler areas were indeed black or dark, and now I've learned that they are not. It's just the filtering.
Yeah, same here.
Yep. Now, how would you see that? How would you get confirmation of that? Out in Arizona, there is a solar observatory that they dim down the sun by a little bit, but you have to essentially wear welder's goggles to see it, and it directly projects the sun onto a white cement tabletop. And the tabletop is about 25 feet across. And it's not only very bright in there, it's very hot in there. So they have to keep, not air conditioning won't even do it, just keep a constant flow of air moving through that room. Giant fans at the far end just sucking the air through there. And I've been in that room, but they were working on the optics at the time, so I couldn't see the sun, but I saw pictures of when they were doing it. And yeah, you can see the disk of the sun. You can see the sunspots. You can see the white areas, the plush, the granulation of the sun. And you can see that the area inside the sunspot, the umbra, is not black. It's just not as bright.
Which observatory is that?
I forget the actual name of it. It's under the auspices of University of Arizona. They have a bunch of observatories, telescopes on a mountaintop. And
it's not the one in Flagstaff, is it?
No, it's not Flagstaff.
Oh,
No.
okay.
If you just search for Solar Observatory Arizona, you'll find it.
I'll do that.
Yep. If you ever get out that way, I highly recommend taking a visit, because there's so many amazing telescopes so close together, and a lot of them are historic. They're older telescopes because the mountain's always been there, and they've been building telescopes on that mountaintop for a long time. So you can actually see the advancements in not just the imaging technology, because they can always swap out a camera, put a new camera in. You can see the advancements in the mount systems of the telescopes. If you remember, they had fork mounts and yoke mounts and German equatorial mounts and all these various kinds of telescope mounts that allow you to have the telescope track for compensating for the Earth's rotation. And you can only build a telescope so big before the counterweight is like a mountain unto itself if you've got a German equatorial telescope. But if you make it an altazimuth telescope, you can make the telescope bigger, 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 and there's no enormous counterweight that follows behind you. But now your image rotates. So on the back end of the telescope, where the imager is, the imager has to actually slowly rotate the camera on the back of the telescope to compensate for the field rotation as the Earth rotates and the telescope transits across the sky. So when you see all these newer, bigger telescopes, none of them are German equatorials. They're all altitude azimuth, because you can only make it so big before you just can't hold that much weight. Okay. I knew it was going to be a short one.
Yeah.
Any comments or questions before I stop recording?
Nope.
Hearing nothing.